University, Japan. I will talk about results from the first 8.5 years of operation with CALET. This is a member of CALET collaboration. It's an international collaboration among Japan, Italy, and the United States. CALET stands for Calorimetric Electron Telescope, designed to carry out direct measurement on the International Space Station. The instrument was launched on August 19th, 2015 by the Japanese H3 rocket and then placed on the Japanese experiment module exposed facility. CALET has two detectors, calorimeter and gamma ray burst monitor. Also, as support sensors, it has advanced stellar compass, GPS receiver, mission data controller, and so on. The total mass is about 600 kilogram, and the telemetry speed is 600 kilobit per second. This is an overview of the CALET, main detector of the CALET. It's a 30 radiation length deep calorimeter designed to detect electrons and gamma rays to 20 TeV and cosmic rays up to 1 PeV. The detector consists of three sub-detectors. From the top, charge detector, CHD, imaging calorimeter, IMC, and total absorption calorimeter, TASC. CHD is made of two layers of plastic scintillator paddles to measure the charge of the incident particles. IMC is made of scintillating fiber belts and tungsten plates to measure arrival direction and initial shower development. And TASC is made of PW scintillators for energy measurement and identification of electrons from the background protons. The features of the CALET detector is the deep thickness and imaging capability. They provide an excellent energy resolution of 2% for electrons and gamma rays, and strong capabilities of identification of electrons from the background protons. These are examples of event candidates of electrons, gamma ray, proton, and ion. Since the start of operations, CALET has been accumulating scientific data without any major interruptions. The left figure in the left, red line in the left figure shows the total lifetimes from the beginning of operation to the end of April this year. And the right figure shows the energy deposit distribution from 1 GB to 1 PeV. One of the features of the CALET is a very wide dynamic range, 6 order of magnitude. The total number of triggered events is more than 4.5 billion events. Again, the CALET detector is optimized for the measurement of electron plus positrons. Thanks to the thick calorimeter and careful calibrations, the energy resolution is less than 2% above 20 GB, as shown in this figure. And thanks to the imaging capabilities, the total background proton are less than 10%, only a few percent, up to 7.5 TeV, with a constant efficiencies of 70%. This is an example of 3 TeV electron candidates and corresponding background protons. This figure shows the BDT distribution for the electron discrimination between electrons and protons compared with Monte Carlo simulations. Then this is our latest results of electron plus positron spectrum from 10 GB to 7.5 TeV compared with MS02 and Dampe and Fermirat. So as you see, our result is very well consistent with AMS02 up to 2 TeV, although the detection method is completely different, calorimeter or magnetospectrometer. On the other hand, the spectral index of Fermi and Dampe is slightly harder than ours. So unfortunately, we have unknown systematics. So for the interpretation, we applied the spectral fitting. At first, about the spectral break at around 1 TeV, we applied the broken power function and the exponential cutoff power functions. The significance of both fits of softening spectrum is more than 6 sigma. So this break can be explained by the energy loss during the propagation. Furthermore, we applied the possible spectral fit in whole energy region with the positron spectrum by MS02. The positron excess, in this model, positron excess is explained by pulsars. And at the TB region, we have considered individual possible nearby sources, such as Beta, Cygnus loop, and monogem. At the TB region, the spectrum indicates a possible contribution from the Beta SNR, with assumption, assuming of the energy output of 0.8 times 10 to 4, 10 to the 48th erg. Next is about the observation of cosmic ray nuclei. With excellent charge identification of individual elements, CALET is exploring the table of elements in the multi-TeV domains. So far, we published the spectrum data of proton, helium, boron, carbon, oxygen, iron, and nickel. The observed energy reaches to 100 TeV or more in the total energies. One of the features of the measurement, nuclear measurement with CALET is charge identification. So as you see, we can clearly identify each element, proton, helium, boron, carbon, nitrogen, oxygen, and iron, and nickels. And another feature is energy measurement. The CALET calorimeter is very thick for electron with 30 radiation lengths, while 1.3 interaction lengths for protons. So we cannot avoid the energy leakage, and energy resolution is 30%. So we need, in order to obtain primary energy spectrum, we need to apply the energy unfolding by making this kind of response matrix by simulations. So then we carried out the beam test at CERN SPS to assess our Monte Carlo simulations. This is an example of energy distribution of carbon 150 GB compared with our simulations. We have checked the accuracy, and the remaining discrepancies are included into the systematic uncertainties. For the systematic uncertainties, we have studied various sources of the systematic uncertainties. The right figures are systematic examples of systematic uncertainties of helium and carbon as a function of energy. The one of the dominant source of the systematics is the Monte Carlo difference of the simulations. We have studied EPIX, Fulca, and JANT4. But the systematic errors is at most 10% or so. Then this is a proton spectrum from 50 GB to 60 TeV. So as you see, we clearly observe the spectral hardening at around 500 GB and the spectral softening at 10 TeV. This is proton spectrum, and this is helium spectrum from 50 GeV to 250 TeV. So like protons, we observed clear hardening and softening. The energy of hardening and softening is same with protons in rigidity. This is a proton to helium ratio as a function of energy per nucleon in left figure and as a function of rigidity in right figure. The spectral index of helium is harder than that of proton by about 0.1 in the whole rigidity region up to 60 TeV. Next is the energy spectra of carbon, oxygen, and boron in 8.4 GB to 3.8 TeV per nucleons. The bottom figure, in the bottom figure, the absolute value is normalized at around at 10 TeV. The primary cosmic rays of carbon and oxygen show the same energy dependence, and they hardened in 260 TeV as 260 GeV per nucleons. And the secondary cosmic rays of boron is clearly different from carbon and oxygen, and the flux hardens in the same energy, but the delta gamma is larger than the case of carbon and boron, carbon and oxygen. This tendency is very well consistent with the results of MS. And this is a boron to carbon, boron to oxygen, and carbon to oxygen ratio. The carbon to oxygen flux ratio as a function of energy is well fitted to a constant value 0.9. So this indicates that the C and O fluxes have the same energy dependence. And boron to carbon and boron to oxygen are in good agreement with MS02, but slightly lower than Dampe results above 300 GB, also consistent with the errors. Then we applied this is a spectral fit of boron to carbon and boron to oxygen. By single power fit, gamma is the spectral index is minus 0.376 plus minus 0.014, and double power fit delta gamma is 0.22. Fit energy region is above 25 GB per nucleon. So in addition, we apply the leaky box model fit. In this model, the boron is produced by carbon and oxygen only during the propagation. According to this fit, the residual path length is 1.17 gram per square centimeter. This is energy spectra of iron up to 1 TeV per nucleon and nickel up to 240 GB per nucleons. The ratio of nickel to iron up to 240 GB is constant with respect to the energies. So this indicates that the iron and nickel has similar acceleration and propagations. And this is a fit to the spectra of iron and nickel. Up to 240 GB, nickel can be fit by single power function. And for iron, the significance of fit with the double power is not sufficient at present to exclude the possibility of a single power. So we are now carefully studied this hardening for the irons. Summary. CALET observation has successfully been carried out for over 8.5 years. And this mission is extended to 2030 with the approval of JAXA. That's all.
Any questions?
Now, well, you have plenty of really interesting data, but let me start with the exposure. You showed at the beginning the exposure for heavy ion or nuclei is much larger than for electrons. What is the reason for that? I mean, this slide number 2 or something, you showed the effective aperture of the instrument. Yeah, on the upper left. So why is it so much larger for nuclei than for gamma rays, electrons, and light nuclei? You see, from 1,000 square centimeters it goes to 4,000.
This is a special trigger mode for ultra heavy nuclei. Only for ultra heavy, above ions. So,
yeah, but what means special trigger mode? So that's the interesting part then. Yeah.
As for ultra heavy, it's measure only the abundance ratio only, like tiger or super tiger. So this do not measure energy. So acceptance is very large.
Okay, so you sacrifice the energy measurement and then you take just everything you get. And this is the reason why, yeah, okay. And okay, why have you not released the intermediate elements? You have got the heavy ones around iron and the very light ones. The light ones are very difficult for the hadrons, of course, because you have you have a calorimeter that has only a small part of it, but the intermediate ones should be easy to measure, right? But you haven't done that.
Yeah, like nickel and so up to iron or nickel, the S omega is same.
Oh,
no, that's not.
No, we can discuss it afterwards, but I think you showed that there's you have a number of elements, primaries you haven't analyzed yet. And I'm only asking why this is the intermediate range of elements that is missing. But okay, yeah. Yeah, no, if you go, yeah, exactly here. You showed you go up to oxygen and then you have nothing, and then you have iron, nickel. You see?
Yeah.
You have not silicon or whatever, which should be easy, right?
Analysis on iron is very easy because the very less background. And carbon oxygen is dominant. So these are the less background, so it's easy for the analysis.
Yeah. Okay, yeah, thanks a lot.
More questions? Not in Zoom. Do you have a reason for the difference in the iron spectrum between you and AMS, which is quite different, as I've seen in your slide? 21, I think.
I don't know. It's not only so I don't know its answer, but for electrons and electron, proton, and helium, the absolute value, the spectral shape and the absolute value is very well consistent with AMS. So the reason of the discrepancy between AMS is not related to the lifetime or geometrical factor or such kind of primitive sources.